Hi, this is Dr. Nerz in my office. This is lecture 3, November 20. It's for the week of November 21st, 2011. This is kind of our Get Caught Up lecture. Okay, so you really have to use these to get sort of caught up because we're a little behind. What happens every time we do, we start doing formal reactions, people get very sluggish with it. And you have to kind of like accept the fact that you got to drill yourself a few times with them and do them over and over, and they're going to start to make sense to you. They really are. Okay, so this is my third lecture. The first two I went over a bunch of, not a bunch, but maybe 4 or 5 reactions. There's one reaction I haven't done yet, which is ozonolysis, and I hope to do that after we get back from Thanksgiving. I'll do it when I do oxidation. But what I want to start to introduce you to are a group of reactions that go together called SN2, SN1, SN1, or E2, and E1. I just want to start getting you into this. We're going to spend a few days on this. All right. These are in chapter, you should start reading chapter 8 of Loudon. So we're going to try to do as much of chapter 8, and more importantly, much more important than that, this is sort of just an introductory. More important, you can actually leap here if you want to. Go to chapter 9. We're really going to do as much of 9, 10, and 11 as we can. All right, I don't know how much we're going to get done. All right, but we're going to get all the fundamentals down. Okay, so I want to give you the fundamentals in this one lecture. So, what's going on with these reactions? You've already done one in lab. SN2, SN1, E2, E1. Well, this is a group of competing reactions. They actually compete with each other, okay, for product formation. And one of the things you should realize is they really all occur together, but in certain situations, one dominates over the other, or certain ones dominate over the others. And that's what we want to learn how to do, is how to predict them. So what does this stand for? Well, the S stands for substitution. The N stands for nucleophilic. Remember, that's my favorite term, nucleophilicity. You know what that means already. A nucleophile is something that loves the nucleus, or protons. Okay, the 2 means bimolecular, and the 1 means unimolecular. And then last but not least, E means elimination. Again, a group of competing reactions because they have somewhat similar conditions. Okay, but different outcomes, very different outcomes. And in certain circumstances, you could have almost all SN2 occurring or almost all E2 occurring. Okay, so what I'm going to do in this particular little video is just go through each one and give you an example and say some things about it. And then I may talk a little bit about part of the reaction called the leaving group. Okay, so let's erase this. This is chapter 9. 8 is just kind of a real overview. Okay, so let's start with SN2. SN2 is kind of like the classic reaction. You did one in lab last week. In an SN2 reaction, you have some kind of a substrate. The substrate has an L on it. An L is just a leaving group. What is a leaving group? A leaving group is a group that likes to leave, that likes to come off. Okay, and then what you add to it is some nucleophile. And in one step, the nucleophile comes in, knocks the leaving group out, and you end up with this substrate nucleophile attached, and just the leaving group free, floating around. Now, what's great about these reactions is they really involve 2 bases, and you can use your knowledge of bases to kind of figure them out. In other words, the reaction should go in the direction that forms the weaker base. That's what we hope. All right, so let me show you an example of this, of a real SN2. So here's a typical SN2 reaction. Okay, very, very, very typical. So you might have a halide like this, and let's say I add sodium methoxide. Okay, and maybe I'll put it in methanol. I'll talk more about solvents in class next week. Okay, but maybe the week after that. But how would you work on this reaction? Some of your flashcards have you doing this right off the bat, like just figuring these out. This is the kind of reaction you can figure out if you know something about acids and bases. So what would I do? I would take these apart, and I'd say, first of all, this is sodium plus, and this is methoxide minus. Okay? Do you know what time it is? I just don't want to miss church.
It's 9:30.
Oh, that's great. Okay. So what would you do with this? Like, what could you tell me now with what you've studied? I hope you could tell me now that this is a strong base. Okay, why? Remember, I told you if you have a concentrated or an isolated charge, not delocalized charge, on oxygen, carbon, nitrogen, okay, or hydrogen, it was a pretty sure bet that you had a strong base. Now, is this the strongest of strong? No, because it's on oxygen, but you do have an isolated charge. So you'd look at this and you'd say, this is probably pretty reactive. It probably wants to attack something in this molecule. Now, what's different about this molecule is it doesn't have any suspicious hydrogens. It doesn't have any hydrogens on oxygen. It doesn't have any hydrogen on nitrogen. It doesn't have any allylic. Remember allylic hydrogens? No allylic hydrogens. What is the most delta plus point in this molecule? It's this carbon right here. This carbon is delta plus. So what you would predict here is not some kind of proton reaction. You would predict a Lewis base reaction. So instead of plucking an H off, because again, no allylic, no H on O, this comes in and hits that carbon. That's what we call the alpha carbon, and just knocks the bromine off, kind of like hitting a hydrogen. What's the upshot of that, or the outcome? The outcome is that this group is now hooked to the carbon, and the byproduct is this bromine. I'll get out of the way. This bromine, which has a negative charge. So it's like our charge went from so if you were just doing the acid-base analysis, you'd say base to base. Which base is weaker? Bromide's a weaker base. So this makes sense. We're kind of going downhill in terms of energy. What happened? What happened was we had a substitution. This group substituted for that group. It was nucleophilic, which means this was looking for positive charge, or nucleus. Okay, and it was bimolecular because, and we're going to talk about this more, but bimolecular means it all happened in one step. So this means one step. Okay, the kinetics for this reaction are that the rate of the reaction equals K, which is a rate constant, times the concentration of the substrate times the concentration of the nucleophile. Okay, that's what bimolecular really means. It means in the rate determining step, the substrate and nucleophile are both involved. And what that leads us to believe is that it's all happening at once. In other words, the nucleophile comes in, the leaving group leaves. Kind of like our acid-base reactions that we were writing. Okay, so that's kind of the classic one. And as you move along in your sheets, you'll find you'll be able to do these pretty easily. Okay, now, what about an SN1? When does an SN1 occur? Okay, so let's look at how it's different. So supposing I change the substrate. So it was this, and I'm going to show you things that are related, okay? And I added, instead of adding sodium methoxide, I just added methanol. I just want to show you how different this is. And let's say methanol is also our solvent. I could just put it as a solvent. Now the way SN1s work, generally, you've got the substrate and the leaving group. And what happens is in the first step, which is the rate determining step, the leaving group just leaves. You get some kind of a substrate cation. Carbocations are coming back to haunt you. And then in the second step, the substrate cation reacts with the nucleophile, whatever it might be, to form the substrate nucleophile. So there's a different rhythm to this reaction. This is a fast step, this is a slow step. Now let's look at how this is different. Okay, first of all, if all I've got is methanol, I don't have a strong base, right? A strong base is when you have a concentrated charge on an atom. Do we have this here? No. This is methanol. It's kind of like water. It's not very reactive, so it's just going to hang around. So this is a weak base. Again, how do you know that? There's no concentrated charge on an atom, okay? So the weak base has no, I always say it has no, what was the word for it? No motivation or no sense of urgency, okay? Or I used to call them slacker bases. In other words, this is just hanging around, being a weak base. It's not attacking anything. It's solvating the molecule, and that's about all it's doing. Okay, now, so nothing's going to happen here from the base, okay? So what has to happen first? Well, what has to happen first is that irresistible carbocation has to form. Now, what's different about this substrate? What's different about this substrate is that it's tertiary, okay? It's not, the last example, my substrate was primary. This is tertiary. Tertiary substrates are very prone to form carbocations because they can form tertiary cations. And as we learned, the activation barrier to form a tertiary cation is lower than to form a primary or a secondary. So what happens in the first step is this leaving group just leaves. Now that really bugs people. They're like, how can a leaving group just leave? But think back to our last one of our last reactions, which was HBr. In peroxides, there were places we were breaking bonds there without anything pushing the group out. Bonds break in large part due to energy. Okay, so we're heating this thing, and in heating it, this leaving group's just going to leave. It forms the nice weak bromide and the carbocation. Okay, now again, is this a very favorable process? Not tremendously so, but you're heating it, and the cation is fairly stable. This is a tertiary cation. Now you should note that everything we've learned about cations here will apply. That you learned about cations with double bonds will apply here. So in other words, cations will rearrange. They'll do all the funny stuff they did before. This cation is not likely to rearrange because it's tertiary and its neighbors are primary and secondary. So again, this doesn't look like something you'd want to do, but it really happens if you heat it up. Some of these bonds break and you make some cation. Now as soon as you make the cation, this is the second step. As someone in my class famously said recently, this base, which is weak, it's kind of like water. This is a solvolysis. So what that means is the ocean is made out of methanol. It's like you're in an ocean of methanol. So this bromide kind of gets lost in that ocean. And statistically, it's much more likely that this methanol will attack than anything else in the ocean. So this base, which is weak, finds this charge irresistible, grabs that, and that again is in the words of someone from the class, and we end up with this. Now notice, this is kind of like a protonated water, like we saw in addition reactions. What you'd want to do is proton exchange that proton off. But all you have is methanol. You can't just throw water in there. There's no water in this reaction. If there were water, the water would be attacking this cation. So this is a purely methanol. I want you to start thinking of methanol as being like water. This will just kind of taxi cab or exchange that proton off. And we will get this, which is an ether. Now, interestingly, it's very similar to the product I made in the last reaction, but it's really came about in a very different way. Again, why is this? Because the base is weak. It has no impetus to attack the substrate. So it waits around till the substrate loses its halide and forms a relatively stable cation. Okay? All right, so let's look at another example. We've got two more. What time is it?
13, almost 14
really?
minutes.
Okay, so let me see if I can get through these. The other two reactions we want to consider are E2 and E1. Okay? Now in E2, what happens is you have... oh, by the way, in the SN1 I just did, the kinetics are such that the rate equals little k times the concentration of the substrate only. Okay, so that's why I wrote it that way. It's saying the only molecule involved in the rate determining step is the substrate. So let me see if I can do a little bit with elimination. So for example, supposing we're looking at E2. Okay, what's an E2? An E2 is a bimolecular elimination, and these compete. So for example, if I had this, I'm just going to show you, I'm going to go right to the example instead of being general. Supposing I had this molecule. I'm trying to make it very similar. Them all look kind of similar to the first example. And supposing I added sodium methoxide, I'm using the same base I used in the first one to attack this one. Okay, now let's think about this. Always look at the base first. So if you looked at this base, you would say it's sodium plus O minus, right? Sodium plus O minus. And you would tell me that's a strong base. You wouldn't pay much attention to this. This is just the solvent. So here's the problem. You'd say, well, this molecule does not have any clearly acidic or suspicious hydrogens that I would abstract with that base, because that's what you're used to doing. You'd say, I'd want to attack this carbon because this carbon is the most delta plus carbon in the molecule. But there's a problem. The problem is it's tertiary. And tertiary, so this has this great impetus or this great urgency, sense of urgency to attack that carbon. But the problem is tertiary carbons have steric problems, meaning they're very crowded. And even though this would love to just hit that carbon and knock that halogen out in one step, it can't do it. The other thing is it's too impatient to wait around for this to form a carbocation as in the last reaction. So what does it do instead? It does the next best thing. It attacks what are called the beta hydrogens. So this is the alpha carbon, this is the beta carbon, these are beta hydrogens. It closes the gate. This is almost like the exact reverse of an addition reaction. And then the leaving group leaves. So this is a way you can do everything very rapidly, but not hit that ridiculously hindered carbon. So it's hitting something that's more accessible. Now, why the beta hydrogens? Because they're electronically related to that leaving group. When these flip in, this is closing the gate, those just come off. Look how much that is like adding HBr. So what's the outcome of this? The outcome is that you would make an alkene. This is a way to make alkenes. Okay, and you get that as your product, and your byproduct would be HOCH3. Now really, try to write that out. All right, again, why did that happen? Because the base is really strong. It wants to attack right away. It can't fit there, so it pulls the next best hydrogen, which is the one next door, which upon removal, the electrons can migrate in and knock that group out and make the alkene. And again, think about what happens when you add HBr. It's the exact reverse of that. Okay, last but not least, okay, E1. Now, E1 always competes with SN1, okay? And so it has a similar condition. So when I wrote SN1, I should have also written E1 occurring with it. So once again, say I draw some kind of tertiary halide. But again, instead of putting the strong base in, I just put methanol in, and this is a solvolysis. Now, I'm going to say this many, many, many times over the course of the next couple of weeks, but when you don't have a strong base, if you're in weak base, the base will not attack the molecule. So the molecule is just, the substrate here is just kind of sitting around. All right, so is this substrate capable of forming a carbocation? Yes. Okay, so this slacker base, no sense of urgency, weak, just solvating this, you're heating it. What's the first event? The first event is this group pops off, okay? It doesn't pop off all of them at once. You know, you just get a certain percentage of carbocations. Now again, the carbocation finds this irresistible, but the other thing that can happen is that in the second step, another way it can stabilize its charge is for the alcohol to simply pull this proton off and allow these electrons to migrate in to form the double bond, resulting in an elimination, okay, plus a protonated alcohol. Now you might wonder about this. This is kind of hard to grasp in a way. You might wonder about it, but the truth is, oh my goodness, when did he come over here?
He just came over.
I'm just going to show everybody my puppy, since I'm almost done. Whoa, this is my new little puppy boy. He just woke up from his nap. Look at him, his name's Henry. He's very cute. He was just coming over to hear the lecture.
Why'd you give it to me all along?
You got him? Okay, I'm almost done. Okay, so that's Henry. Someday I'll bring him in. But anyway, this, okay, it's kind of weird because you would think, why doesn't this just go in here? But remember, this is the rate determining step. The rate of the reaction only depends on the concentration of substrate. And that being the case, it doesn't really matter how this stabilizes itself. If this is the highest barrier in the reaction, it doesn't really matter. Okay, so that's enough to keep you busy for a while. Again, read Chapter 5, start reading Chapter 9. I'll see you in class. This, again, is the third lecture for the week of November 21st, 2011. Thanks for watching all these. Bye.